All right, hey, Honors Geometry. Mr. Clark here with a little explanation of the week 4 assignment. You guys just make sure you're patient with radicals. It's a new skill. If stuff didn't go that great for week 4, we're gonna, use the time in week 5 to correct that. All right, so let's just start with number 1 here. So the first one, we have the square root of 128. There's all sorts of factors you can go with in the factor tree. I ended up, just seeing that it was an even number and using 2 as a factor, and 2 goes into it 64 times. So with my factors of 64 and 2, 2 is a prime number, so we can stop that branch right there. 64. There's plenty of ways you could factor that, but, if you remember that a number is a perfect square like 64, go right to that. So I separated 64 into 8 and 8. So we have a pair of 8s. 1 8 comes out. We have a 2 by itself. No other 2 in sight. That's going to stay home. So we got 8 root 2, or 8 radical 2 for the answer. Looking at B, we have negative 3 root 12. Now, some people struggled with if you have a number in front of the radical. Remember, that number stays on the outside, that negative 3, and then whatever comes out of the radical, whatever we can factor out, is going to end up getting multiplied by that negative 3. So we have 12 inside the radical there. I separated it into 3 and 4, and then 4 is a perfect square, so I knew that we had 2 and 2 as factors of 4. So we have a pair of 2's, so that means that 1, 2 is going to come out. That's the term that's going to end up getting multiplied by that negative 3. So remember, don't forget about that term on the outside. It's going to be part of making your solution. Back to the factor tree. This 3 never got paired off with anything, so it's staying in. So we got root 3 right there. So we got negative 3 on the outside times that 2 that came out gives us negative 6. And then we have that 3 in the radical. So negative 6 root 3. All right, looking at C, we have 5 on the outside. So remember, don't forget about that. So 98, even number, divided it by 2 and got 49. 2 can't be broken down any further. 49 was a convenient number because it is a square. So that breaks up into 7 times 7. So 7 has a date. It's going out. 2 does not have a date. It's staying in. It's staying home. So we got 5 on the outside times that 7 that came out gives us 35, and then that we have radical 2 attached to it, so 35 root 2. Looking at number 2. Now, when we multiply radicals, remember the outside terms will get multiplied together, the inside terms will get multiplied together. Anything that can be factored out, of course, will get multiplied by the outside terms. Now, 2a, this one, there actually wasn't a ton to do. We have negative 2 times 4 on the outside, so we didn't forget about those. Looking at root 5 times root 7. 5, it's a prime number. 7's a prime number, so we only have 5 and 7 for our factor trees there. That is not the same number, so there's nothing we can circle. The 5 and the 7 stay home. You can multiply them back together, and we get 35 there. So the negative 2 times the 4 on the outside gives us negative 8, and then nothing came out of the radicals, so root 5 times root 7 gives us root 35. So negative 8, root 35. All right, looking at part B, this one was a little bit more interesting because we did have stuff to do on this one. Looking at the outside, we have the 5 and the 3. We don't want to forget about those. If you want, you can go right down to the bottom and write those down right away just so you don't forget about them. And then we're going to factor tree the root 3 and the root 6. Now, the way that I think of it, even though it's 2 radicals multiplied together, I think of it as one giant factor tree. So we have a 3 come down from the root 3. That's the only factor, 3 and 1. We don't have to bother, using the 1, though. If we look at 6, we got 3 times 2 to make that. So looking at our factor tree, we have a 3 at the end of this branch, a 3 at the end of this branch. We've got a pair of 3's. A 3 is coming out. And then we have 2 by itself. That will be staying put. So on the outside, we had that 5 and the 3 from earlier. We have the 3 that came out when we factored the radical. And then we have, the 2 that's staying put. So 5 times 3 is 15. 15 times 3 is 45. And then root 2 is along for the ride. All right, so number 3. Now, this way is a little bit longer. I'm going to show you that you have options here. I'm going to show you a shortcut on the next page that I think you guys will like more. All right, so approaching this, guys, you can start off by just factoring the numerator and then the denominator. For the numerator, we got root 25. It's going to break up to 5 and 5. It's a square. We know that that's just going to be 5. For the denominator, the root 50, that breaks up into 25 and 2, and 25, we just factored that, it's going to be 5 and 5. So in the denominator, a 5 comes out, but the 2 never had a match, so the 2 staying put. So right now we have 5 over 5 root 2. Now we need to rationalize that denominator, because remember, radicals are not allowed in the denominator if we're talking simplest radical form. So we're going to multiply by the radical from the denominator over itself, root 2 over root 2. Because remember, back to class, if you multiply by something over itself, you're really just multiplying by 1. You know, it's a weird-looking 1, but ultimately we're just multiplying by 1. So we don't change the value of anything, we just change how it looks. All right, so 5 times root 2 up top for the numerator, just 5 root 2, glued together by multiplication. 5 root 2 times root 2 on the bottom. Remember, the square root of anything times itself, that number is going to come out of the square root. So we end up with 5 times 2 on the bottom now. So 5 times 2 gives us 10. Now we're very close to being done, but remember, we got 5 root 2 over 10. We got to simplify the fraction if possible. You can double check the radical if you want. Nothing else is coming out of the 2. But we do have 5 over 10 here, which is the same as 1/2. And then you don't even really have to write the 1, so we end up with root 2 over 2. I would accept 1 root 2 over 2, though. That is fine. All right, so like I said, I have a quicker way. So looking at number 3 another way, remember that if you have a radical over a radical, you can actually combine those to being under one radical like I did here. So now I got the square root of 25 over 50. Now I can reduce a fraction inside the radical. So 25 over 50, that's the same as 1/2. So I got square root of 1/2, which is now I'm gonna separate them back into 2 radicals. I got square root of 1 over square root of 2. So we got to rationalize the denominator like we did before. This time we're dealing with much smaller numbers though, because we already reduced everything. So we're going to multiply by root 2 over itself. Root 1 times root 2 gives us root 2 on top. Root 2 times root 2 is going to give us 2. So we end up with root 2 over 2. And I'd say, that way it was a little bit quicker. All right, jumping over to number 4. So now we're adding some radicals here. So remember, you can't add 2 radicals together unless you have the same index, which in here, they're both square roots, so that's good. But then we have to have the same radicand as well. So right now we got 63 and we got 7. We can't add them together the way that they are. But maybe, if we're lucky, when we simplify the radicals, they'll match up. So root 63, I thought of 9 times 7 right away. So we have 9 and 7 for the factors. Breaking 9 up into 3 and 3. 9's a convenient factor because it's a square. So we got a pair of 3s. 3 comes out. 7 by itself, it's staying put. So we still have that 4 on the outside from the beginning. So that 3 that came out gets multiplied by the 4. We got 12 root 7 there. Now, 9 root 7, nothing's coming out of 7. 7's a prime number. It's staying put in the radical. So we can just jump down to the bottom here. We got 12 root 7 plus 9 root 7. And remember, it's just like x. Like if you had 12x plus 9x, you'd have 21x. Notice how the x doesn't change at all. So just like an x, the root 7's kind of along for the ride by multiplication. So 12 root 7 plus 9 root 7, that would mean we have 21 root 7s. So the answer there, 21 root 7. Looking at B, this one we have 2 radical 50 plus 7 radical 98. Both of these radicals can be simplified, and they're both pretty convenient. They're both even numbers, so 50 I'm going to switch to 25 and 2. The 25 breaks up into 5 and 5, so we have that 2 on the outside to begin with. We got a pair of 5, so 1 5 is coming out. 2 does not have a match. It's staying home. Looking at 7 root 98. 98 we're breaking up into 49 and 2. When we look at 49, it breaks up into 7 and 7. It's a square, so that's convenient. So we already had that 7 on the outside. Now, because we have a pair of 7s, 1 7 comes out to get multiplied by the 7 that was already there. And then 2 did not find a match. It is staying home in the radical. So 7 times 7 is going to give us 49 root 2 there. So we end up with 10 root 2 plus 49 root 2. And again, remember, root 2 is along for the ride, so we have 59 root 2 for that solution. Looking at 5, we got a right triangle here. We're missing the hypotenuse, so solving for x is going to be by itself when we use the Pythagorean theorem. So we square out 7 and 6. We got 49 and 36. Add them together, you get 85. Now this one I saw some mistakes because I think people panicked when nothing came out of the radical. So remember, Square root of 85, some factors there. We have 5 and 17. Now 5's a prime number, so nothing's happening there. 17's a prime number, nothing's happening there. So neither of these numbers have a match. So don't force it when this happens, guys. Don't think like, oh, I better take a 5 out or I better take a 17 out. There's not a pair of either one of these. There's just one of each. So they actually stay inside the radical. So you can take the step and multiply them back together under the radical, or we can remember where they came from. It all started as root 85. So x is going to be root 85. That one actually could not be simplified any further than that. Looking at B, we got a Pythagorean theorem. This time we're missing one of the legs instead of the hypotenuse. So remember, the hypotenuse is always by itself. So we got 20 by itself there. So we set up the Pythagorean theorem. 14 squared gives us 196. 20 squared gives us 400. We're going to subtract the 196 over and get 204 equals x squared. Remember, we're looking for x, so we got to take the square root of both sides. Now this one, we will have a little bit come out at least. A lot of people might have started with 2 and 102, and you can do that. You can go from there. Remember the factor tree. There's a lot of different paths to end up at the same destination. I started with 4 and 51. 4 is a square, so we can break that into 2 and 2. 51 has factors. We got 3 and 17. Now, we have a pair of 2s, so a 2 is coming out. We don't have a pair of 3s or of 17, so those 2 are staying put. So they're actually going to get multiplied back together inside the radical. So the 2 comes out. We get the 3 and the 17 back in the radical. We multiply them together, and it brings us back to that 51 that they came from. So we got x equals 2 root 51. All right, looking at 6. It's another Pythagorean theorem, and again, we're going after a leg. So the hypotenuse is by itself. So we put 15 squared by itself when we do a squared plus b squared equals c squared. Crunching it out, 5 squared is 25. 15 squared is 225. Subtract the 25 from both sides. We're going to get x squared equals 200. Take the square root of both sides. I broke it up into 102. And 100 is a square, so I knew that 10 and 10 would be the factors there. So we got a pair of 10s. 10 comes out. 2's by itself. It is staying home. So we end up with 10 root 2 for our answer. So 10 root 2 feet. All right, so 7, I believe this was the word problem inspired by the movie Holes. So we had Stanley Yelnats carrying 0, 4 miles north and 2 miles east. Remember that north is, you can think of that as up, east is to the right if we're, thinking in terms of direction. So we got 4 squared plus 2 squared equals x squared. We're trying to figure out what the straight path would be lengthwise. So 4 squared is 16, 2 squared is 4. Combine them and we get 20. X squared equals 20. We got to take the square root of both sides. 20 can break up into 2 and 10. 10 can break up into 2 and 5. So we got a pair of 2's. 2 is coming out. We got a 5 by itself. It's staying home. So our answer is going to be 2 root 5. And should have my label there, miles. All right, let's see. Oh, so this was the converse of the Pythagorean theorem, being able to classify a triangle, by its angles using the sides. So looking at the first one, we set up, remember the longest side is always by itself. A squared plus b squared question mark c squared. We don't know how it relates to c squared. Now I have a couple ways to remember this. So let me write this down real quick. A squared plus b squared is greater than c squared. A squared plus b squared is less than c squared. And a squared plus b squared equals c squared. All right, so when a squared plus b squared is greater than c squared, the way that I remember it is more is less. So a squared plus b squared is greater than c squared. It's more than c squared. And the less part is acute would be the smallest type of angle. So I remember that again with more is less. If it's greater than, it's going to be the lesser type of angle, acute. Now, a squared plus b squared is less than c squared. I remember this using the opposite. Less is more. Those common sayings. So when less is more, less than obviously represents less. More is going to represent, the biggest type of angle out of the three, obtuse. So a squared plus b squared is less than c squared means it's an obtuse triangle. Less is more. A squared plus b squared equals c squared. Hopefully we remember that just by knowing that, we've only used the Pythagorean theorem in the past with right triangles because a squared plus b squared equals c squared is only to be used with right triangles. So, hopefully that one's kind of, been ingrained in our memory at this point. So remember, more is less, less is more, equal is right. All right, so looking at 8a, when we set up the Pythagorean theorem there, we end up getting 32 compared to 25. So 32 is greater than 25, more is less. It's an acute triangle. Looking at B, this example worked out the same. We got 12, the hypotenuse by itself, or the potential hypotenuse. So when we crunch this out, you should get 181 is greater than 144. So again, more is less. It's going to be acute. Looking at part C, this one ended up being a Pythagorean triple. When we do a squared plus b squared, it ended up being equal to c squared. We get 22,500 on both sides. So because we got the equal sign there, it is a right triangle. All right, so that's the explanation of the homework. Let's put that to use with week 5. So we're gonna try some more examples next.